Now the sum and product to the roots of, well, to start off with a quadratic, and we've seen this idea before. So if alpha and beta are the roots of this particular quadratic, then we know it could be factorised like this. X minus alpha would be a factor, x minus beta would be a factor, but it's not monic, so I'll need to multiply by a out the front. So they would be the same. If I expand the right hand side out and group my terms together, I can create this relationship that the sum of the roots, so alpha plus beta, would be minus b on a, and the product of the roots, so alpha times beta, would be c on a. That was useful for this sort of question. So form a quadratic equation whose roots are 2 and minus 3. I don't have to worry about forming the factors and expanding the whole thing out. I can just write the answer down, because in my head I'm saying, well, look, I know the sum of the roots would be minus 1. I know the product of the roots would be minus 6. Therefore, that must be my equation. X squared plus x minus 6 equals 0. And of course, it's very useful when the roots are irrational like this one. 2 plus root 5, 2 minus root 5. Because the sum of the roots, the irrational part cancels out, we get 4. The product, difference of 2 squares, we get minus 1, and so there's our equation. So we have played with that idea already. But we can now look at some other interesting problems. If alpha and beta are the roots of this quadratic, we don't want to actually go to the bother of solving it. I just want to work out, well, what's the sum of the roots? Now I use that idea in reverse. Oh, well, minus b on a, 3 on 2, there it is. What's the product of the roots? Again, I don't have to go and solve it. I can go c on a, it's minus a half. But then we can manipulate our roots. What about the sum of the roots squared? What's alpha squared plus beta squared? What I can do is I can use my formula that we know for the perfect square, but just rearrange it and make alpha squared plus beta squared the subject. And these two things I've already worked out. I could substitute straight into that and I get my answer, 13 on 4. Another sort of common question we see is, well, what's the sum of the reciprocal of the roots? That becomes an algebraic fraction question. And then look at the numerator and look at the denominator. Again, it's things we've already worked out. So I can substitute in and get our answer. We have a quadratic, but we just don't know what that constant number at the end is. We want to work out what that is. But we've been given some other information. One of the roots is double the other root. Well, instead of the roots being alpha and beta then, I'm going to call them alpha and 2 alpha. The sum of the roots now becomes just 3 alpha. And the product of the roots would just be 2 alpha squared. I can work out what the root is very easily then, because 3 alpha is negative 6, alpha is negative 2. That allows me to work out m, because that's 2 alpha squared. Substitute into that one, and I've got the constant number is 8. That's a quadratic. But we're interested in any type of polynomial. So we've seen for quadratics, sum of the roots is minus b on a, and the product of the roots is c on a. Well, what about the cubic? The interesting thing is the sum of the roots is still minus b on a. That doesn't change. The product of the roots is no longer the product of the roots. What it is the sum of the roots, but taking them 2 at a time, so all the possible pairings. So I've got alpha, beta, alpha, gamma, and beta, gamma, but that will still be c on a. Product of the roots for this one now is alpha, beta, gamma. It becomes minus d on a. What about a quartic? Again, the sum of the roots is still minus b on a. The sum when I take them 2 at a time is still c on a. Now when I do the product, it's not the product anymore. It's just all the possible triples. Alpha, beta, gamma, alpha, beta, delta, alpha, gamma, delta, and beta, gamma, delta, but they will still be minus d on a. The product of the roots now becomes e on a. And this pattern just keeps going. So for any polynomial we like, we can say, and in shorthand notation, rather than writing down every root, I can just use this shorthand notation. The sum of the roots, so capital sigma, that's the symbol we know means sum, and we just write alpha down, that's the first root. So the sum of the roots, one at a time, is always going to be minus b on a. It doesn't matter what the order of the polynomial is. This we just then call sum of the roots, but 2 at a time, taking all the possible pairings. That will always be c on a. 3 at a time will always be minus d on a. 4 at a time will always be e on a. And this pattern will keep going. So the next one, if it was a pentic, then I'd have the sum of the roots 5 at a time. it'll go to negative, it'll be f on a, and so on, and so on, and so on. This relationship will still always be true, of course. So the sum of the roots 1 at a time squared will always be the sum of the roots 1 at a time all squared minus twice the sum of the roots 2 at a time. That will still hold. So let's do something. Here's a cubic. For some reason we're interested in finding the value of 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma. I'm not sure why we're interested in that particular result, but there you go. We're interested in finding that out. Well, 1 at a time will be 5 on 2. 2 at a time, although I don't really need it for this one, will be minus 3 on 2. And 3 at a time will be minus a half. Well, we want 4 times the one where it's 1 at a time minus 7 times 3 at a time. We have the answer. The reciprocals of those roots. Again, it's an algebraic fraction question. We end up with, on the top of the fraction, the sum of the roots 2 at a time over the sum of the roots 3 at a time. Sub in what we found for those and we get 3. There's the square one. Love asking the square one. Alpha squared plus beta squared plus gamma squared. And what we said was, well, hang on, that will still be the sum of the roots 1 at a time all squared minus twice the sum of the roots 2 at a time. Substitute that in. Ooh, here's a very old HSC question. So alpha, beta and gamma are the roots of this particular cubic. Find the sum of the roots. Be careful. It's very, very easy to make a mistake here and just go, oh, that's going to be 3 because you're just looking at the first number. But notice there is no coefficient of x squared there. The coefficient of x squared is 0, so the sum of the roots 1 at a time is 0. They then asked for the product of the roots, or sum of the roots 3 at a time. Okay, well, we can look at that. That's negative 1. They asked for the reciprocal. They're all very common questions, you see. So, okay, algebraic fraction. Sub in 2 at a time, which would be negative 3, and 3 at a time is negative 1. It's known that 2 of the roots of this equation are reciprocals of each other. Find the value of k. So 2 of the roots are reciprocals of each other. So I'm going to let the roots now be alpha, 1 on alpha, the reciprocal of that root, and beta. So there's my 3 roots. Now the product of the roots here is going to be the useful one to start off with, because when I multiply a number with its reciprocal, it's just going to be 1. That allows me to find beta straight away. So I know one of the roots of this equation is minus 3. Now I can just use my factor theorem, because if minus 3 is a root, I know that when I substitute it in, I'll get 0. So if I substitute in, and we can find k, 13. And that saved me mucking around with all the other roots 1 at a time, 2 at a time, and so on. 2006. Ooh, okay. X cubed plus rx squared plus sx plus t. They've given us the zeros 1, but then alpha and minus alpha. Find the value of r. This time the sum of the roots 1 at a time is going to be useful because the alpha and the minus alpha will cancel out, leaving me with the sum of the roots just being 1, and that's going to equal negative r. r equals negative 1. That one comes out quite nicely. But the next question, they weren't actually interested in what s is and what t is, but just what the sum of those two things are. So find the value of s plus t. Well, if I look at the sum of the roots 2 at a time, because that's going to get s into it somehow, and I end up with s is minus alpha squared. But I also need t, so let's look at 3 at a time, and I get that t is alpha squared. Well, we want s plus t. It's just going to be 0. Of course, I could have done it another way. I could have said this: hey, you've told me that 1 is a 0. Therefore, it satisfies the factor theorem. Polynomial 1 will equal 0. And if I substitute that in, we've already worked out r is negative 1. Therefore, s plus t is 0. That's possibly a little bit quicker than the other way. There are different ways we could approach that question. So playing around with the roots and the coefficients of polynomials.